Some people, by the way, if their dental fittings aren't done correctly, have been known to pick up radio signals in their fillings in the teeth, but they can't control which program they listen to. So just to bring out and remind you again what we're really doing here. You've got so used to seeing with that little rainbow of light, and we're beginning with instruments to extend beyond it. And the moment we do that, we realize there's this whole symphony in nature that we are now beginning to hear, whereas previously we only saw a little bit of it. So what I want to do now is to go beyond the blue horizon to the ultraviolet and X-rays and start seeing what things show up with that. Now what we've got here is a photograph of the sun taken in the optical spectrum. You can see the sunspots on there. This is typically what you would say the sun looks like. You're used to the sun being this round yellow ball and occasionally dark sunspots in it. But that's what it looks like in the spectrum of light, the rainbow. Let's go beyond the rainbow and see what happens if we look with X-rays. Now what we see here is that there are incredibly hot swirling gas around the surface of the sun that's radiating much more in the X-ray wavelengths than in the optical wavelengths. And these things were completely invisible to you if you were restricted to the rainbow of light. We can go and look at it in ultraviolet light. And what do we see now? There's this huge flare. And out here, you see the size of the Earth by comparison. So you've discovered the presence of this huge flare, which must be hundreds of thousands of kilometers long. If you looked at the sun just in the rainbow, you would be totally unaware that that was there. So again, the question, what is reality? Is there a flare or isn't there? If you look in the rainbow, you wouldn't be knowing it was there. But the moment you can open up that piano, you see that there's much more going on than previously you'd realized. And this is all since 1945. Now let's stick with that rainbow for a minute and see what's happened in astronomy. Let's go back to the originator of modern astronomy, Galileo. Galileo, around 1600 or so, turned his telescope on Jupiter. And he saw this beautiful image in this telescope. Here is Jupiter. Now, you will see Jupiter, a bright object in the night sky at this time of the year. And if you too have a telescope, you'll be able to see these 4 points of light, the moons of Jupiter, or 4 of the moons of Jupiter. And if you watch them from one night to the next, they change their position. What's happening is this, that just as we orbit around the sun, and our moon orbits around us, so the moons of Jupiter are orbiting around Jupiter. And from night to night, their relative position is moving. And so these spots of light will change their position. When Galileo first announced this news back in the 17th century, people didn't believe him. In fact, he was even worse than that. He was accused of being a heretic. He was accused of inventing things that didn't exist in the universe. That these things only existed in his telescope. They weren't real. And he had a real bad time as a result of that. But now we know that he was right. And we know that he was right because with modern instruments, we can go and see for ourselves. We can send spacecraft all across that intervening space, travel to Jupiter and look. And we see here are the moons of Jupiter with the planet in the background. And we can even look up better than this and see here a lump of rock whirling in space right across there. Galileo's point of light has become a real lump of rock whirling in the cosmos. So Galileo was seeing reality. He had just extended his vision. He could see things that had previously been outside the range of vision, but they were real things that he was revealing for the first time. Now, this business about reality is going to be a very important message for us, because during these programs we're going to be going deeper and deeper into matter and devising more and more sophisticated instruments to shine radiation on smaller and smaller things and detect them in new ways. We're going to be inventing new spectacles to see the smallest things. We will be seeing reality. We will not be inventing things any more than Galileo was inventing things. This is real stuff that we're going to see. Well, today we're on the trail of atoms and molecules, and what we would like to do is to get an idea of how far we have to go. How big are these molecules that we're on the trail of? Well, to lead into that, let's do a little game that I used to do as a child, which I never really understood, but I think I'm beginning to catch out what's going on now. Have you ever played with a sheet of paper and just tried folding it and seeing how many times you can fold it? You know, each time you fold it, it gets twice as thick as it was before, and eventually you get to a point where you can't fold it anymore. In fact, I folded it here about 7 times, and that's my world record. I have never ever been able to fold that piece of paper more than 7 times. As a young child, I thought if I kept folding it, I might reach the moon and climb all the way up there. But I never got further than this. So I began to think, why is it I can't fold it more than 7 times? Perhaps it's because the paper wasn't big enough. Maybe if I had a piece of paper that was twice as big, then the first fold would get it to here, and I'd have one more, and so on. It doesn't work. So what we're going to do today is to see what would happen if we use a really big piece of paper. So can we have a really big piece of paper and see if we can beat my world record? Thank you. And can we have a couple of volunteers to help me? Hands going on all over the place. Would you like to be a volunteer? You come down here with the piece of paper, and lady right up the back there, about 7 rows back with the fair hair. There we are. You can be the other end of the piece of paper. What's your name?
Howard.
Howard. Right, Howard? You're Mary. Hello, Mary. Right, if you could stand one at either end of the sheet, and one of you keep it still, and the other one fold one piece over. Let's see how many times you can fold this piece of paper. So this is the first fold, and press it down, because you're going to try and beat a world record, and you're already 1/7 of the way there. Right. This is the second fold. That's 2. That's right, I might lose count, so help me in the audience if you can. 3. Oh, we're getting there. 4. Now this is even bigger than the piece of paper I started with, so you must be with a good chance. Right. 5 coming up. Whichever way you like. 5. The audience will judge whether you've succeeded or not. I don't want to prejudice them in any way. 6. Getting a bit nervous here. Right. My world record's in danger. One more fold. Can you even reach 7? 7. Right. One more fold and you've beaten me. Oh. All right. I think time is to call time out. Thank you very much. Thank you very much. Well, my world record is thankfully still alive. It does raise the question, though, why is it? It doesn't matter how big that piece of paper is. You don't seem to be able to bend it more than 7 times. Now, what's going on? What's going on is this, that the paper is made of molecules, and the molecules are held together very strongly. That's what gives things their shape. It's what gives us our shape. And every time you fold that piece of paper, at the corner, you're pulling some molecules around further than they want to be. And after about 7 folds, you're trying to drag them around this huge corner. You're trying to pull them apart, and the molecules won't let you do that, unless the paper tears, of course. So you're seeing that there's a certain point where the molecules won't go any further at all. That's what stops the paper folding more than 7 times. But that gives us the clue as to how we can measure the size of molecules and get a number on this. And what Bryson is going to do now is to show us how to do this